Hello everyone and welcome to our presentation. I am Mehdi Ahmed and I will be walking you through our work on benchmarking accuracy energy trade-offs in lightweight spiking neural networks with a focus on our pruned Spiking SqueezeNet. Unlike traditional artificial neural networks that processes information through continuous activation, SNNs mimic the brain by communicating through discrete spikes. Neurons fire only when their membrane potential crosses a threshold, and this is called event-driven processing. This makes SNNs highly energy efficient because they consume power only when spikes occur. They are also compatible with neuromorphic hardware like Intel's Loihi IBM's TrueNorth, making them ideal for edge development. To understand why this matters, consider this example running a traditional CNN on a smart glass at 13 frames per second. The battery lasts only about 64 minutes. That's simply not sustainable for always on edge applications. This energy bottleneck motivates our exploration of SNN alternatives. So, what did we do? We systematically converted several lightweight CNN architectures, for example, ShuffleNet, MnasNet, MixNet, SqueezeNet, into their SNN counterparts. We replaced railway activation with leaky integrated-and-fire neurons and trained using surrogate gradient descent. Then, based on initial results, we identified SqueezeNet as the best performer and applied a structured pruning strategy. As shown in here, we removed entire fire modules that were redundant, retaining only the most effective ones, which are F4, F6, F8, and F9 modules. Let's look at the results. This table compares all CNN models across three datasets, Cypher 10, Cypher 100, and Tiny ImageNet. On Cypher 10, our pruned SqueezeNet achieves 81% accuracy and a 6% improvement over the baseline SqueezeNet, while actually reducing energy consumption from 0.0355 to 0.0295 millijoules. This pattern holds across Cypher 100 and Tiny ImageNet, where SqueezeNet Prune consistently outperforms all other lightweight SNNs. Notice how MixNet is extremely energy efficient but sacrifices accuracy while XceptionNet consumes huge energy without proportional gains. Now, how do these SNNs compare to their CNN parents? This table shows the accuracy energy trade-off on Cypher 10. CNNs generally achieve slightly higher accuracy but a massive energy cost. Look at MixNet. The CNN version consumes 15.7 times more energy than its SNN counterpart. For SqueezeNet pruned, the CNN achieves 82% accuracy and SNN achieves 81%, just a 1% drop, but the energy consumption is reduced by over 5.6 times. This is the Pareto optimal sweet spot we are aiming for. How do we decide which modules to prune? We conducted a systematic ablation study on Cypher 10 and table shows different pruned schedules. Head-heavy pruning removed later layers, achieving decent accuracy with low energy. Tail-heavy pruning, which preserved deeper modules and performed better up to 79%. But our refined alternating strategy, retaining F4, F6, F8, and F9, achieved the best result, 81% accuracy with only 0.0295 millijoules. This confirms that deeper spiking modules carry stronger discriminative power. Why does pruning work so well? Look at this gradient flow visualization. Before pruning, the middle layer's gradients collapse near zero, a classic sign of gradient starvation. After pruning, gradient flow becomes more healthier. The early and middle layers receives stronger gradients, reducing vanishing effects. Pruning enables balanced gradient propagation across the network, which directly translates to better learning and higher accuracy. Compact, pruned SNNs are not just energy efficient curiosities, they are practical, high performance alternatives for edge deployment. Future work will extend these methods to larger datasets and validate performance on actual neuromorphic hardware. Thank you for watching the video.